There are lots of new things happening in today's electric grids, like electric vehicles, like AI data centers. Also, it's good opportunity for us to look at that, and we have to. We cannot go back to the power system from 50, 100 years ago to address today's system. We have to look at the grid structure and the grid operation to deal with those challenges, provide more sustainable, resilient solution for the future.
Welcome to the Project Report. Join your host, Elyse Dzenick, as she sits with researchers and highly qualified personnel working on FES-funded research. Explore what they're working on, why it matters, and what's to come.
Today, Dr. Ryan Lee from the University of Alberta's Department of Electrical and Computer Engineering is joining me to talk about his research center, the Elite Grid Research Lab, and how they are supporting energy security in Alberta and around the world. Can you tell me a little bit about Alberta's electricity grid? Are you looking at all levels, generation and transmission and distribution?
We're looking at almost all of them, but it can be at different scales. The Alberta system is a large system, but even in the smaller scale, even on campus, we may have power generation, we have power delivery, we have loads. So that's kind of like a microgrid or smaller grid. So we're definitely looking at the full generation, transmission, distribution.
How does your work contribute to energy security in Alberta?
I think we focusing on how to integrate renewable-based power generation and the new loads in today's power consumptions, where the consumers side of the system. For example, the electric vehicles and lots of discussions on AI data centers, how much power they consume. So we look at those new loads and how they can be integrated to the grid. How do we supply power to those loads and integrate renewable energy and the storage? I think that will, if we are able to integrate all of them in a very resilient way, so that definitely contribute to the energy stability or security of the system.
What's the biggest difference in integrating renewables versus natural gas?
That's interesting question, because for renewable energy, first of all, I think it's easy to understand. For solar power, as example, during the night there's no power output, so it's not really controllable. The wind power, very similar. When the wind is strong, you have more power produced or generated, but when the wind is low, it's hard to generate more power. For traditional fossil fuel based, like natural gas based power generation, is very controllable. So you can control the output. Actually, for power system or stability, lots of the studies is how do we make sure the power generation is same as the load demand? Because if they're not the same, there might be a great stability issue here. So the challenge is how to integrate this renewable into the system and consider the nature that are not fully controllable.
What's the benefit of researching why and how we can integrate renewables and diversify our energy resources?
I think the biggest benefit is with the diverse energy sources. We really improve our energy securities. No matter what happens, we'll have a very sustainable source of energy supply. And if you have strategy to how to integrate them in a very reliable, resilient manner, I think that's good for not just Alberta, for Canada and the world as well.
So what is the difference between AC and DC energy?
Yeah, AC, we call it alternating current. In North America, we know that when we turn on the volts outlet, it's a 60 hertz, 120 volt in the residential system. So that's a typical AC. Resistors can be both voltage and current, and our power system is basically powered by AC. DC is a direct current, so which means the voltage and current, they're kind of constant, it's not alternating. And the example for that is battery. And the new technologies like energy storage and the electric vehicles, those are powered by batteries. And some of those renewable-based power generation like solar panels, their output is DC. So there are lots of DC-based technologies now being integrated to the power system. Another challenge for these DC-based technologies, lots of them, they don't behave like traditional AC-based power generation, because there's not a whole lot of momentum. Because you have a big AC machine that's rotating, there's a big momentum. In power system, people say that's inertia. So with a good inertia, that helps with the system stability. But for lots of solar-based energy storage, like battery-based power generation, so they don't have that rotating inertia into the system, which means they can stop power generation very quickly. So that may cause stress to the system if it's not prepared and controlled properly. So that's another challenge we're dealing with through control and coordination. We do want to transmit that electricity at a very high voltage so we can reduce the current, reduce the loss on the lines to improve the efficiency. And transformer at that time, they're based on AC technologies. They can step up the voltage to improve the efficiency of the system. But these days we have AC to DC voltage converters or voltage conversion device. They can do that voltage level conversion just as easy as a transformer. So that's why it's relatively easier to integrate DC-based technologies these days also. At the Elyse Grid Lab, we focus on the AC-DC voltage conversion and how to convert the voltage in a very efficient way. And then the second part of that, how do we control this process? For example, if there's a solar panel, the output voltage is DC, how do we integrate that to the power system through AC-DC voltage conversion, and also how do we control the power flow? Same for energy storage, and very similar for like electric vehicle charging and the battery energy storage, charging, discharging control. So how do we coordinate all these devices and all these control to make sure the whole system works together with the traditional AC power system in a very seamless manner?
How do you do that?
It's a combination of designing those DC AC voltage converters and designing not just the device itself, but also how do we control them. Maybe take one step back to talk about stability of the system. So if there's a disturbance, can the system operating point back to original operating point or close to it? Where if you lose that point or you move to somewhere completely different, then we say the system is unstable. So with that disturbance, it's very important for the system to deal with that properly. For renewable-based power generation, for energy storage with the DC-AC voltage converters, lots of them, they cannot provide very high capacity to deal with that large disturbance, which means they may have to stop operation when they see a disturbance, and that may cause additional disturbance to the system. So that is the challenge. So there are lots of research now in my group and also in many other places globally to look at how do we control those systems so they behave closer to the traditional AC system so they can be integrated in a better way.
What is a prosumer grid?
Prosumer, I think that word is a combination of two words, right? So producer and consumer. So in the power system, we say there are generation, transmission, distribution system, and the load. Actually, for the load side, there we call them consumers. Can be residential, commercial, industry sectors. But if those consumers or load side, they also produce power, we call them prosumers. One example is if you have a solar power generation on your rooftop, and at the same time you have your loads at home and maybe electric vehicle charging, and then energy storage in the garage, that's small grid. So we say, now you're a prosumer. If you're a prosumer, then you have to consider your own power generation, your own load consumption, and there's opportunity to maximize the benefits by owning all of them. More than 20 years ago, my PhD research topics is on microgrid. So basically microgrid is leveraging renewable-based power generation. At your home, if you have your own solar power generation and have loads, so we can consider that as a nanogrid. It's so small, or microgrids. And these microgrids can be connected to the system most of the time. But if there's a blackout, so that microgrid structure gives you more resilience. Another example for microgrids in Canada, there's lots of them. There's probably 300 or more than 300 off-grid communities. So these communities, each of them we can consider them as a microgrid. So they have their own power generation, their own loads there. And these years, you will see that there are more projects in those communities to leverage solar power and energy storage to reduce the fuel consumption for the diesel generator because they're so expensive for fuel delivery, for fuel handling, and renewable energy actually can make a business case in those communities. But again, how do we address different type of power generation and loads all together in the microgrid operation? So that's a good research topic we've been working on for many years.
How does your team work with artificial intelligence?
AI is a topic that's everybody's discussing now. I would say in the electric grid, there are two aspects. We call it AI for power and also power for AI. Start with the AI for power because artificial intelligence can really help the grid operations. For a grid operation, there are lots of data available. Let's say you have solar generation, you have electric vehicle, energy storage. How do we utilize those historic data or real-time data to help us to operate the system in a more reliable, more resilient way? So that's AI for power, just one example. There's many other applications there. On the other hand, those AI data center, they consume lots of power, hundreds or even thousands of megawatts power. And how do we provide power to those AI data centers? So that's a very important topic because the load of a big AI data center could be just as big as Edmonton. When we're talking about the loads keep increasing, it's hard to keep up. Then how do we deal with that? The AI data center power consumption. So that's another topic that's very relevant. So we're looking at how to power those AI data centers in a more efficient way, maybe using our microgrid operation concept to have generation very close to the load so the data center doesn't have to draw lots of power from the grid. So that can be one solution. And we're looking at how to do energy storage in the AI data center because the load characteristic of AI data center is very, very different from traditional data center.
Yeah, AI and its associated energy demand are really popular topics right now. It's really interesting to hear that you're incorporating that sort of thinking down the line in your research nowadays. How long have you been working on renewable energy integration with the Elite Grid Lab?
For the Elite Grid Research Lab, actually we set it up with the good infrastructure support about 7-8 years ago. So that really gave us opportunity to do more multidisciplinary research. For example, how do we work together with the AI experts on utilizing that power to operate the grid better, and how do we work with the other researchers for example, with the mechanical engineering background, with chemical engineering background to do clean energy integration and look at the wider range of issues to solve today's challenges.
What's next for the Elite Grid Research Lab?
I think we'll continue with what we're doing and look at this hybrid AC and DC system because for now, in the past 100 years, we have the very AC-dominated power system, and you see lots of DC-based technologies being integrated to the system, even for data centers. Lots of discussions on DC-powered data centers because lots of these computers, servers, GPU, they're powered by actually DC voltage. And we'll continue to look at that. For now, it's a hybrid AC-DC. And maybe 20, 50 years later, the system will be DC dominated. And we'll look at the system structure, the AC-DC conversion technologies, as well as the system operation strategies. We'll have high percentage of renewable energy and new loads connected to today's power system. Actually, University of Alberta, I spent 18 years here. I think lots of my research is actually done here, and all the students and the collaborators with the Elite Grid Research Lab, they really contribute significantly into our research. This is not possible without, again, smart students that we have, but also the industry partners from utilities and from manufacturers and small, medium-sized enterprises, because they're the key for driving innovations together in this area.
Well, thank you so much for sitting down and chatting with me today about your research. It's been really interesting to hear how the Elite Grid Lab is working to integrate renewables. And
Yep, thanks for having me. My pleasure.